all this stuff was preliminary were preliminary statements to the solution of the problem that obviously were needed, but now we have to construct the weak form, to state the weak form. And to state the weak form, as we have unknowns as velocity and phi, so phi is, at the place of phi there is p. So this is what we have called phi. Okay. So u is the velocity unknown, p is the pressure unknown, v and q are the corresponding test functions. Okay, and I'm also specifying the loading. F is okay, it's the vector 1, 0. So it's exactly this vector here, which is in fact this one. Okay. So now the weak formulation, so we have to write the weak formulation. Just let's try to write it here, and then we recognize it there. So essentially, what if you remember, what we did was to multiply this equation by a suitable test function for the velocity, no? So we call the u, in fact, the unknown, and v the test function. So essentially, what we are doing is this: mu Laplacian I of Laplacian of ui minus, let's call it this p using the nomenclature that we are using over there, and this f minus p comma I equal to fi. So what we are doing is to multiply by vi this and integrate. No? This is the way in which we write the weak form. No? So what do we have? So if we manipulate a little bit this first term, we have already seen, but vi Laplacian of ui, Laplacian is the divergence of the gradient. So in the end, this will be minus the gradient vi, the gradient of ui, plus the divergence of of gradient gradient ui vi, no? Check. Divergence gradient of ui, yes. Divergence gradient of ui. And so this, when you consider the integral of this and that over the domain, so this is over omega f, this part goes to the boundary of omega f, so this is the boundary of omega f of what? Of gradient of ui dot n vi, where the the u is the unknown, and the v is the test function. So if you remember, we said plenty of times that this part goes to 0 because of what? Because of the fact that the vi are test functions verifying the same Dirichlet boundary conditions as the ui, so they are 0 on the fifth part. So the ISF does not contribute to this integral. Moreover, on the parts where we have periodicity, the ui and the vi are periodic, n is, so the gradient of ui is still periodic, n is anti-periodic, and so when you sum up this with that, you get 0, when you sum up this with that, you get 0. So this integral doesn't provide any contribution. No? So in the end, from the first term, you have only this. Okay? When you integrate by parts, in the weak form, you have minus mu integral over omega f of dvi by dzj dui by dzj. Okay, and this is just the first term, but then you have this, and this you have to keep. So you have minus the integral over omega f of what? Of vi p comma I. So this is the scalar product between the velocity and the gradient of our unknown pressure. And it remains like that, equal to the work of external forces, which is this. Okay, Fi Vi. So this is what comes out from here. So the unknown is u, I, but it is also p. Okay. Obviously, we have also this second equation that we didn't use at all in our previous analysis, because we were looking for solutions having zero divergence. So we somehow just restricted the space of solution to functions verifying this condition. But here we are not doing that. So as we have multiplied this equation for a test function v relative to velocity, we have to multiply the second equation for test function q relative to pressure. So we have this equation, but we have also this equation, integral over omega f of q ui comma I equals 0. Okay, so the unknowns are ui and p. The test functions are vi and q. Okay, and so you see what is written what is written there. You see what is written there. You have that in fact, what do we have? We have to identify. Now we need to specify the problem as a bilinear form. No, if you remember, what we wrote was that we didn't have this term in the previous analysis, and we said that this was a bilinear form in the velocity. No? Saying that we were evaluating it over a test function and a trial function, so a test function and the solution of the problem. Here, I'm the idea is that we have to extend this because now our space of solutions and space of test function is not just velocity, but it is velocity and pressure. So we have our bilinear function, which is this AUFL, which is involving this contribution, that contribution, and this other contribution here. Okay, because it involves trial function and test function for velocity, trial function for pressure and test function for pressure, trial function for velocity and test function for pressure. So you see that it's a kind of matrix involving the inner product, the scalar product between the gradient of u and the gradient of v in dx, the p and the divergence of v, and this is the first line, and the second line is the q, the divergence of u, while there is no contribution involving q and p. There is not an integral here, there is no contribution like pq, no? Okay, and so here I put none. So this AUFL is just a matrix way to prescribe these two, let's say, the left-hand side of these two equations, no? Because for the moment I didn't introduce the right-hand side. So this is the bilinear form. So essentially we are writing the problem in this way. A of trial functions, test functions, equal to L depending on F. In fact, L is just this, is the linear form of the test functions parameterized by the loading. So it's L of the test functions. Okay. So if you remember, the ancient form was this, was just mu, in fact, was this equal to that, without this and without that. Because we were restricting our analysis to the case where test and trial velocities had zero divergence. This is no more the case, and so we have to incorporate this second equation because it's not automatically verified, it's not for free. Okay, so we have this A, which is prescribed like that, this L, which is prescribed just with this term, because in principle there should be another term involving loading on pressure times test function of pressure, but this is zero, and so we don't put at all. And in fact, you see that LUFL is the inner product between F, which is the vector 1, 0, and V, the test function, times the volume element, Vx, and this is a zero form. It's a way to assign zero for the Q. Okay, so this is the way in which we have defined the the weak formulation with this force. Okay, then here there is just a preconditional that is introduced, that this is useful but not fundamental from the point of view of developing the technique for solving. It's just to better catch the solution. And then I define I introduce the linear solver. So in fact, the linear solver, I'm not going through all the specification of this part of the code, but this this linear problem defines the problem that we have to solve. So you need to give to this function the A, so the the bilinear form, the L bilinear form, the space of constrained this constraint space you are looking for the constraint space where you are looking for the solution. So this MPCD and MPCQ was the restriction, the restriction that we introduced in order to incorporate periodic boundary conditions. So this is the syntax that is used to take into account periodic boundary conditions. Then the boundary condition, the additional boundary conditions on the fifth region that we call BC naught. And okay, here as we have introduced this preconditioner, also the preconditioner. Then you, so here, in fact, there is a delicate point here, which is related to the fact that in order to solve for the pressure, we need to restrict the space where we look for the solution of the pressure to the solution minus the null space. And what is the reason of that? The reason is that according to this, to the way in which the problem is stated, you can get a solution of the problem which I mean the solution, let's say this, the solution of the problem in terms of pressure is not completely known, because you can add a constant to the pressure and you will never observe any difference between the solution that you will get with this constant equal 0 or this constant equal to whatever you want, no? Because the only term in which pressure appears is here with the gradient of pressure. So in fact the point is that there is a null space, a kernel in the space of a solution for pressure, which is which corresponds to functions, to constant functions that should be subtracted, and so this is done here. But I don't want to enter in these details. So essentially here we solve the problem in terms of U and P, and we save these unsuitable files, XDMF files, for velocity and pressure, and we also calculate the what is it? Yes, here I'm also calculating the average of velocity. So UH0 and UH1 FEM form is the integral of UH, of the first component of UH and the second component of UH, so the first and the second component of the velocity field, the average over the cell, which is our target, because I remember you that Kxx was 1 by omega, the integral over omega f of v d omega f, and Kyx, this associated to alpha 1, and Kyx equal to 1 by omega integral over omega f of v2 associated also to alpha 1 d omega f. So as here omega is a cell or a square of a unit square, sorry, this 1 by omega is 1. So I just did this, when you find this FEM assembly scalar, you have seen, I have shown you before, you are doing the integral, and this FEM form is the form obtained via the scalar components, the second scalar component of UH times dx. Okay, so these UX average and UY average are the average velocity, the average of the x velocity, the x component of the velocity, and the average of the y component of the velocity, which will provide kxx and kyx. Okay. Okay, so just to conclude, then we will come back on this next time. So let me see. So in the end, now we have the file is ready, and so we have just to run the script. So Python 3 is just the way to launch a Python file, and then the file itself. Okay, and so you see that it gives me the UX average velocity, which is 0.02, let's say, and the UI velocity, which is almost 0, 10 to the minus 7. Okay, so what we got is that this has a certain value and this is 0. So if we can, then we will come back on this next time, but we can have a quick look via ParaView to the solution. The velocity. So for instance, this is the solution for the x component, and you see the periodicity. So say this is the dx. Okay, due to the gradient of the unit gradient of pressure oriented like that. This is the vx component that then should be integrated, providing the value of the average that I have shown you before. And similarly for Vy, so the Vy is something like that. We have to come back on this to discuss a little bit about the shape of these plots, in particular about the symmetry, because every time that you find a numerical solution, you have to a little bit check if something that is expected is indeed, some property that is expected is indeed verified by the solution. And also for pressure. So also the pressure is a solution of the problem. Let's see. For instance, something like that. So this is the profile for pressure, which is ranging between negative and positive. Obviously, this is the oscillating part of the solution. So it's not strange that the pressure could be negative, because it's not the real pressure. It's the pressure, it's the oscillating part, the periodic part of the solution for pressure. No? So it's not so strange that the pressure, because obviously you cannot expect a negative pressure in terms of physical solution. But this is, you should remember that the solution for pressure will split into alpha zeta, alpha z plus this solution. So this solution, this part of the P is just the oscillating contribution, which obviously can be positive and negative. Okay, so we have to come back on that, and we have to discuss what happens when we introduce some loss of symmetry within this domain. So what I was telling you last time, introducing, for instance, an hole that we can move around in the domain. So in this way, we can, looking at this solution, we can compare it with our estimates, and this we will do. Obviously, introducing some loss of symmetry, it will be much more difficult to have an estimate to compare the solution. Okay, so think of that. I sent you the GMSH file. I will put also this file that we discussed today. If you have time, it would not be a bad idea to think of how to introduce this hole and how to treat what should be the condition to introduce in such a way that we can discuss this next time. Okay.